Hello and welcome to today's Wolfram Institute live stream. Today we're joined with William Edward Hahn, professor at Florida Atlantic University, co-founder of the Machine Perceptions and Cognitive Robotics Laboratory there, and member of the Center for Complex Systems at FAU. Today he'll be presenting some one-dimensional and two-dimensional cellular automata, and we'll look at some of the interesting patterns that he's found. William, go ahead.
Awesome. Yeah, really. Thanks, everybody. Thanks, Dugan. Thanks, James, for this opportunity. So I'm very excited to share you some of the work I've been working on and some of the motivations behind why I think this is interesting work. Just kind of a rough outline. Won't stick to this too much, but I want to bring up this idea of digital physics, sort of what that means in terms of revolution of how we look at nature. And then we'll spend a good amount of time looking at Stephen Wolfram's simple programs. And that really inspired the work that you're going to see here today. And more generally, just complex patterns. Where do patterns come from in nature? And I want to frame this almost like an exobiology, whether we're sort of looking out into the world and trying to find intelligent life, whether it's natural or artificial, and thinking about the patterns they leave behind. So some people talk about technosignatures, sort of related to the Fermi paradox. And so we'll come back to that, sort of finding examples in the wild. And then that's related to this idea I'm calling natural computers. Do we find computers out in the wild, sort of in the forest, so to speak, not just as the products of technology and engineering, but sort of natural things? And as part of that, I will introduce this idea I call spontaneities. So let's just jump in here. Really, it's about mapping out nature and trying to understand the geometry of the world that we inhabit. And the Greeks in the classic world were giving us some basic primitives, sort of the Platonic solids, if you will, right? Our triangles and squares and circles. But as Mandelbrot, one of the founders of fractal dynamics, fractal geometry, pointed out, the nature doesn't work this way. Nature is not really made out of these shapes. And we need to think about a different kind of geometry if we really want to map onto the natural world. So in general, this idea of digital physics is kind of redoing the physics that Newton gave us. And Newton, he gave us the calculus itself, but then he also gave us the framework where we use that calculus to understand the physical world. And this was used for everything from astronomy to kinetic reactions in biology and everything in between. And so this is kind of the triumph of science. Science itself could be approximated as being the application of these calculus type models, differential equations, partial differential equations, to natural data and to experiments. But now we have a different way of framing the world. We have bits, and we have information theory, and we have quantum information theory. And so it's suspected that we might need to start thinking about the world in terms of a large computer. This is at the core of Wolfram's physics project, in his case, doing string rewriting and graph models. But really, it's the idea of thinking of the primitives of reality as being more like computer programs, which is an idea that wouldn't have been available to somebody like Newton. So it could be that when we zoom in on things, that the world is sort of like a graph paper. It might not be sort of squares like we're going to look at today. It might be more like beer foam, where you have little bubbles and different sizes and scales and more of a dynamic kind of thing. And then when we think of the macroscopic behavior, things like fluid dynamics, we don't see the atoms in the ocean, so to speak. We just see this average analog style behavior, but that could just be the scale that we're looking at. And so that's kind of the idea that I want you to have in the back of your mind, is these simple rules and these simple patterns. And then when you zoom out on them and run them at scale, what do you get? And in particular, these ideas of simple automatons that just look at their neighbors. So what would that digital physics look like? Well, physics is the thing on the left, in this case, turbulence and fluid flow, everything from smoke of a burnt out candle to the giant red spot on Jupiter, these phenomenon where we want to try to figure out why did they emerge and how they operate. And on the right here, we have something called a digital wind tunnel, which is trying to use this digital graph paper. This is not the classic fluid simulation where we're trying to numerically solve differential equations. This is a discrete world where we can have exact update rules and there's no rounding errors or anything like that. So that would be one example of doing digital physics. Another interesting example would be crystal growth, to where we have sort of a nucleation site, a little seed crystal here, and then random atoms in the environment, if they bump into it, then they will effectively crystallize and start growing that crystal. But this isn't a very interesting crystal, not like the snowflakes here. But it turns out that there's another property, the latent heat of water. And so, right, to melt an ice cube, you have to put heat in. And so to make an ice cube, you have to get heat out. And so as these ice crystals form, they actually create little pockets of elevated temperature that prohibits the ice from then growing in that region. And that's how you get this kind of feedback loop that creates the structure. And that can be modeled, where if we take the crystal growth that we saw before as automata, and we model this where you have a site that can't form because one next to it just did, which simulates this latent heat, then we get the kind of symmetries that you see in snowflakes. So the one that I'm most interested in is animal patterns. I think it's quite interesting that Alan Turing, after he invented the computer and did groundbreaking work in AI and cryptography, he then spent eventually the rest of his life studying what he called morphogenesis, and sort of the pattern formation like that we see here, not just on the surface print level. It's not just about camouflage, but the entire body plan itself, our full 3D and 4-dimensional blueprint as we unfold. But to take an example, like in these lizards or even the panda bear, right? Some part of the panda bear is black, some part of the panda bear is white. But every skin cell in the panda bear has the exact same DNA code. And so how is this coordinated where you get these alternating behaviors and complex patterns emerging at this organism scale? And so this is likely going to be the future of computing and robotics in general. I think this is why Alan Turing spent so much time working on it. And so we can build simple models like this. This one's more like an icing model, kind of like that you'd see in magnetism, but it ends up building this kind of stripe pattern where you have the feedback amongst the cells there, even though they all have the same code. So Wolfram just did a Newton-style job. This is kind of like the new Principia of outlining not just a new area of science, but a whole new way of doing science. And it's somewhere in between experiment, mathematics, theoretical physics, and biology, because we're using techniques or approaches, say from naturalism, where we have to just go out and catalog things, and then applying that to essentially theoretical mathematics, theoretical physics, and do these kinds of numerical and computational experiments. As Wolfram describes, the computer is like a telescope or a microscope, and it points us into a whole new area, which would then create new directions for science. So let's review the idea of the simple program. We have a one-dimensional world in this case that sort of lives on graph paper. And what we want to do is we want to think of time as going down in this case. And we want to think of the evolution of this one-dimensional pattern as it unfolds. And in this case, it's like that simple crystal is just going to grow a triangle. But what Wolfram did is he established this paradigm where you can set up each rule as this simple binary pattern. And so when you want to know what one square is going to be, you look at the square above it, and then one to the left and one to the right, the sort of one neighbor away. And then we find that pattern, and then we look up the recipe here, and that will tell us what the square should be. So for this square here, the one above it is filled in, and the two on its neighbors are not. And so that pattern is represented here. And then we see that the resulting new square would be given by this recipe. So what you'll notice is that these collection of the three, they don't change, but down here below, we have the option of choosing whether or not that bit gets turned on or off based on the pattern above it. And so if we change this pattern just a little bit, we can see, you can think of these as all zeros and just one, or vice versa. And then here we have these two as blank, and we get a very different checkerboard pattern. Not very interesting yet, but it shows how this pattern can grow. Now, what is interesting is if we just kind of cycle through these, and we can actually number these. So because of these can be thought of as a binary number, we can convert that number into decimal. And so this case is the 90th rule that you would come across. And now we have a Sierpinski triangle. We have a fractal that kind of showed up out of nowhere. and the beginning of an object that looks more complex than just the 8 bits of program. So this simple program is just defined by 8 bits, and it's not obvious where this fractal came from. It's not obvious that there's a recipe for a fractal buried inside those 8 bits. Another rule, if we go to rule 110 rather, we get more exotic behavior. And amazingly, Wolfram has shown that this is capable of universal computation. And so in an abstract sense, this pattern generating process is capable of simulating any process that you would run on any computer. Sort of this so-called Church-Turing thesis, which would say that once you get to universal computation, they can all pretend to be each other. It might take a very long time to run, and it might be extraordinarily difficult to program, but in theory, this is capable of universal computation. Again, with that fractal, we have this kind of self-similarity that if we zoom out or zoom in, we get back to where we started from, this kind of invariance. And then probably one of the most interesting rules is rule 30, which just kind of generates this unreasonable complexity for how simple the rule is. So again, we have 8 bits of computer program, but when we run this thing, we get a lot of interesting behavior that never repeats. To me, this kind of looks like rain on a window, especially here on the right side. On the left side, it ends up repeating, but on the right side in the middle, this never repeats. And what's particularly interesting is there's no shortcutting this process. So Wolfram calls this computational irreducibility, that the only practical and reasonable way to know what the outcome of this pattern is going to be, say 1,000 steps later, is to just run rule 30. There's no simpler way to do it. Any other mechanism or contraption that would somehow guess what the pattern on some row later is going to be would be much, much more complicated than actually just running the rule itself. And so the machinery required to predict this gets very complicated. And the most practical way by far is to simply just run it. So there's no shortcutting it. There's nothing simpler than the rule itself that will generate this pattern. This is not really true in other areas of physics, like orbital mechanics, for example. You can just take t equals 100 years from now and plug it into the equation, and you can see kind of where things will be. With this kind of formulation, you can't shortcut it. You have to just actually run the program. And so then this gives us the question of where does this complexity come from? Where does this seemingly diverse set of random patterns, is it in the 8 bits? Is it somewhere in the universe? Right. So the breakdown would be that somehow randomness is being injected from outside the environment. Deus ex machina, where somehow angels outside of the universe are pouring random numbers into our universe for some mechanism. Right. That would be one possibility. The other possibility would be from the initial conditions. At the Big Bang, God put all the randomness you would ever need at that initial point. And now we're just sort of reusing and recycling that original randomness that was there. But the third mechanism could be this simple pattern. It could be these simple programs where we have recipes that are only 8 bits or so, but end up generating what looks to an observer as a random sequence. And so it's not clear where randomness comes. And so now we have these 3 candidates to choose from. I think one of the best examples of how these actually show up in nature is the tent olive. These can be found on the coastline quite easily, particularly in North Carolina. And then if you look on these patterns, they're remarkable examples of one-dimensional patterns. And it turns out the shells actually grow in a one-dimensional way. On the leading edge here of the mollusk, it will put out a protein matrix that will be secreted by the organism. And then minerals in the seawater will crystallize onto that to create the shell itself. And so it literally grows with essentially one row of atoms at a time. And amazingly, you get this same sort of one-dimensional growth patterns, very similar to the rules that we just saw. And so what's neat is evolution didn't have to design these per se. All it had to do was sample them. It had to find them. They're already there. And these simple 8-bit programs that evolution could just sort of select from the possibility of of the different programs rather than having to encode that pattern in the DNA. We now see that that pattern sort of emerges from the dynamics. So what's nice is we can then enumerate all of these. And so this is what Wolfram originally did with his computational telescope with Mathematica, is pointed it at this new universe and tried to see what are all these different patterns out there, and can we catalog them, and what other natural systems, whether in plants or animals or even other more abstract systems, should we expect to find these kinds of emergent automata like rules. And so again, I think it's extraordinary that this complexity is not encoded in the DNA. It doesn't have to be stored and selection pressure in that kind of way. We can think of the organism as kind of stumbling upon them by chance, and then you'd get evolutionary pressure to select for these different patterns, which might have camouflage effects or whatever it might be. And so these are some early simulations of that, and then matching the patterns here. So here's a digital shell on the right, and then an actual shell on the left. Okay, so now I want to get really into my main result here of what I've been working on. And I've attempted to generalize these one-dimensional automata by using tiny neural networks to form the update rules, rather than just having this simple 8-bit program. So here is some Mathematica code. We'll pull up the Wolfram notebook in just a second. And what we're going to be doing is we're going to be looking at the same 3 neighbors, just like we did before. But what we're going to do is we're going to map those 3 numbers into a 100-dimensional space as an intermediate. In this case, the 100 dimensions is a variable. As the experimenter, you can choose these dimensions. There's still a lot of work and exploration needs to be done. So if anybody wants to help with this project, we can explore these more systematically. But in this case, we're going to be mapping from 3 numbers, which is the previous cell and your neighbor to the left and right. And we're going to be mapping this with a matrix multiplication to a 100-dimensional vector. And we're doing that with a random numbers drawn from a random distribution from -1 to 1. And these would form our 2 weight matrices. We'll show an equation for this in just a minute. But effectively, we're going to multiply by the first set of weights, which is a matrix that's going to map us up to 100 dimensions. We're then going to apply a nonlinearity typical in neural networks. But in this case, it has the added benefit of keeping the values bounded. So tan H will essentially squish the values between -1 and +1. And so that keeps the whole thing in a bounded region. And then we do another mapping again with the output layer, which will get us back down to 1 number. So we go from 3 to 100, and then from 100 back down to 1, and that forms our new output. So we can take a look at this. This runs in Wolfram Cloud. I've made the link available so that you can try this yourself. Here is just the source code. It's only just these few lines. What do we got? 6 lines of code there. And we can take a look at what this looks like as we run this. I have another tab open here. Let's go up to the top. And so we can see what some of these patterns generate. And so each of these is defined by these 2 random matrices, a 100 by 3 and a 1 by 100. And so these form the basis of the simple program as these 2 matrices. And then we're going to do the tangent H along the way to make it act kind of like a neural network, and also to make sure the values are bounded. So if we just kind of scroll through here, we start to see some interesting patterns, kind of analog or continuous generalizations of the simple one-dimensional programs. And what's interesting is we see this emergence of kind of like topological defects, these kind of pseudo-particles that will emerge and then blend with the other pieces. Sometimes we get very simple behavior, but other times we get richer behavior that just kind of looks either random, or again, these kind of pseudo-particles, which are kind of like the gliders in the game of life, or Ellynne, where you have these stable, kind of like a soliton that will move through this dynamic as it goes. So I encourage everybody to take a look at this notebook. Obviously, the space of possibilities here is too large for us to to catalog, except for doing it in kind of this biological way, right? We want to think of this like a large hadron collider or something like that, and then see what are the space of possible programs, what emerges, and in particular, can we get a non-trivial one to emerge? Can we get something like Rule 110, where we can show that it's capable of universal computation? We'll just kind of scrub through a few more of these where you can see these kind of particles survive for some time and then die out. Some of them look very natural, like minerals, crystal growth, things like that. So now, because we have a simple parameterized model, we could make this differentiable, or to do some sort of genetic algorithm to explore the possibilities, and then have some other system that's trying to identify interesting or non-trivial behavior. But then how do we do that? Do we take a general purpose vision algorithm like we see now with these multimodal vision language models and point it at this? Would it be able to distinguish between interesting behavior and non-interesting behavior? I suspect it might. Can we run these longer? Can we look at the boundary conditions and the different behaviors that might emerge here? So there's almost an endless variety of these. So I'll encourage everybody to download the notebook here, get the link, and then you can try this yourself. All right, so let me show you a couple others I have here. Here's the kind of the equations for this. And so we have our vector X, and we're going to be looking at the neighbors. But effectively what we're doing is we're mapping that with this first weight matrix W1 into this, in our case, 100-dimensional space. And then we're going to do our tan H on that, and then multiply that by our second set of weights. And then we can do a tan H on the end. We don't have to. That's also another choice. And so we could think of this as taking us from our color space. And so for the black and white version, this would be 1 times however many cells we have. And then H is going to be our hidden state. And so we're going to be sort of mapping up into this higher dimensional hidden state. And then we're going to then bring that back down with W2. And then if we do this in 2 dimensions, which I'll show you in a minute, we can generalize this and just use a convolution operator, which is very similar. There's kind of like a nice symmetry here. And we can just extend this to where our little filter is now looking at neighbors like the game of life. It's looking up, down, left, and right. And then we can do the same sort of process. So here's just a few more examples, not in any particular order, just some sort of random ones that came out. And again, you can see that this one will generate a whole array of these. Thank you to Dugan. He helped me organize the loop here, and Eric when we were at the Hacker House up in Cambridge a few months ago. And we'll just flip through here. I like this kind of sort of soft features, right? You get like hard edges, but then you get kind of like blurry bits that seem a little bit more organic. And I'd be curious what we can do with those in terms of building mechanisms out of this behavior. And they tend to look sort of naturalistic in a sense. I'll just flip through these here. And so now we can go through and try to catalog all of these sort of pseudo patterns. So now I want to show you, I made another dashboard for this that you can also run on the web. And there's a few different options here. We can do it in black and white, and we can run this. We can change the speed at which it runs. And then if we hit random, we'll get a different rule set. There is a button to download the rules. If we hit export, this will bring those rules in as a JSON file. I'm still looking at ways that we can visualize those rules. We can then run this in RGB, where each value is 3. So it's a 3 vector for every square, but the matrix multiplication can work out just the same. And again, we can crank this random button to see all of the different behaviors that might emerge. Then what we can do is we can change the initial conditions. So rather than starting at just a single spot, we can start with a random array up top, or we can do some other stuff like put a line in the middle and to see how the initial conditions and boundary conditions affect these dynamics. Then what we can do is we can do this for 2 dimensions. And so let me put this back to the original Delta, and we can run this. I'm still working on the layout for this website, so bear with me on that part. It kind of cuts off the bottom of it. And then we can do this for two dimensions in color. And then what we can do is we can enable a montage and actually show a bunch of these at once. And then we can see the different behaviors that emerge. I'm working on setting up frame skip to try to make it more perceptually easier to look at, let's say. There's a little bit of, dare I say, like an epilepsy warning kind of thing you might issue with something like this. But what's neat is kind of these behaviors, right? Like here we have something that's generating waves, and then it's hitting this other wave front that also seems to be stable in its own sense. We get tessellating patterns. We get stable regions and unstable regions. We get kind of these boundary effects. So lots of interesting behaviors. And these are just kind of like the first pass at the architecture. So we could look at different neural architectures with skip connections like you see in residual nets. I'd like to apply a vision transformer or something like that, which could maybe do some more laundering connections, and then do sort of multi-scale neighborhoods. Right now, we're just looking at a small local neighborhood, but we could look at dilated neighborhoods or multi-scale patterns and so on. Like this one here in blue and yellow is small to see there, but you have these little patterns that are sort of translating from left to right there. And I think that's, again, reminiscent of these gliders and glider guns. And so I think that's worth taking a look at. So this link will be available, and you guys can run this in your browser. So I had the opportunity recently to travel to Spain and to look at some extraordinary architecture and tile work in the region of Andalusia, particularly a place called Alhambra. And it got me thinking about if we are to look at patterns. And in this case, it's a product of a civilization that was here approximately 1,000 years ago. And it still exists, but not in the same way. And if we were to find these patterns, what do we think of the civilization that created them? Traditionally, we would assume that it would have to be an intelligent species, but now we see that we can get very sophisticated patterns out of rather unsophisticated or seemingly unsophisticated computer programs. And so that's why I just want to explore in general how physics creates these patterns. And I really like the idea suggested by Landauer and folks that information is physical, that we tend to think of something like bits as being in this world of abstract ideas in the Platonic realm of computer science. But really, when we look at actual bits, they are always physically represented somehow, as electricity, as rocks, as magnets, as something. And so that means it's ultimately bound by the laws of physics itself. And so if we want to think about these patterns, we really should be thinking about these are no different than snowflakes or turbulence. These are just patterns that occur at different scales of nature. And the fact that humans created them is just sort of an interesting byproduct. So it reminds me of this idea. Richard Feynman said the same equations have the same solutions. I know Stephen Wolfram worked with Richard Feynman on the connection machine project, which essentially was kind of like a cellular automata computer. And there's that work led me into learning more about Feynman and his notion on computation. So he's very famous for his physics lectures. Most physics majors have seen or read his lectures on physics at some point. But I would say just as extraordinary, but he did later in his life, is his lectures on computation, which is the physics of information and thermodynamics and all of that amazing stuff. And something that is close to my heart is the physics of brains, and not just our brain, but abstract brains as they might exist throughout the universe. And in a more larger sense, is the physics of complex systems, how things like these seashells, where you have this interaction between DNA and seawater and evolutionary pressures on the pattern, right? This sort of physics at a different scale, and we need to think about how we model those. So these are two books, the two textbooks I would highly recommend, not textbooks, but collections that I highly recommend. This one is basically his lectures transcribed. It's very good. And then the other one, Feynman and Computation, it's more like a collection of works from other individuals, Marvin Minsky and such, that has some very interesting papers. So I highly recommend it for both of those. All right, so we have these patterns. These are the ones that Wolfram showed in New Kind of Science. And as I was traveling recently, I saw all these, and it hit me like, this is the same thing. But if we were to find these on, say, another planet or next to the red spot of Jupiter, should we assume they're people? Probably at this point, but maybe they're not. Maybe there's something more complicated. Just to be clear, I'm not suggesting that these patterns are not man-made. That's not what I mean. I just mean in general, we want to think about the process of pattern generation in a more broader sense. So here's me at this place called Alhambra. We got to take some of these wonderful pictures. This is not a picture I took, but it's a nice close-up of that building. And in general, we can think of these structures themselves as like an automata. It's a sort of a 3D pattern that, for some odd reason, primates on this planet decide to construct bricks in these shapes. Why? Is that just our neural network? Are we tapping into this larger sort of process like Rule 30 that's already there, right? Do people create arches and columns? Or are these sort of natural shapes and we just sort of found them? They sort of have a ubiquitous presence around the planet to make suggested they are kind of natural shapes, analogous to the fractals or squares or the classic geometry shapes. And so there's an extraordinary variety of these different patterns. And so we want to think of like the process that would generate these. Could we expect to find a process like this somewhere else throughout nature, human or otherwise? And it just brings me to the larger notion of just sort of finding things in the wild, sort of what I call natural computers. So Wolfram's idea of universality with the automata is showing that nature essentially stumbles upon computation rather easily, that the ceiling for universality is rather low, and that nature finds it easily and often. At least the potential is there. And so I'm fascinated by this. What is the chance that you would find a computer in the wild? This is kind of like the monkeys and the typewriters type scenario. Like, what's the chance that the monkeys have actually typed out Shakespeare? That if we were to search, the universe at a large scale, right, at an impossibly large scale, light years and eons, should we expect, or how many, working computers should we expect to find? On this planet, we find a lot of them because we have intelligent life that created advanced industry and all of that. And so we find computers here. But could we find a computer in the seashell? Could we find it in some exotic forest or some faraway ocean where the minerals are in such a way that it ends up forming one of these automaton? And like Rule 110, it happens to be universal. And so then once we find a computer, what's the chance it's doing something interesting? And this gives us the question of what makes a computation non-trivial, what makes it interesting. And I think these are open questions at the heart of complexity itself. And automating that might not be possible or practical, but the idea of digital physics in general is that the whole universe is kind of like a computer. And so then should we find little computers inside that big computer? And if so, are they doing anything interesting? And so I'd just like to think, I don't have answers for that, but just sort of finding these computers out in the wild, and how sophisticated do they have to be before they can do something like the universal computation. So in more general sense, it leads to this idea I call spontaneities, which is kind of like an intelligent life form that exists for no reason, simpler than itself, which is an idea Gregory Chaitin talks about, sort of true for no reason. And if we think about sort of how the vast complexity in terms of dynamics we would expect to see across the universe, should there be something that just by chance happens to be something interesting? And maybe it's fleeting. That's this idea I have of ephemeral computation. It maybe only lasts for seconds or even less than that. But in some solar flare in the plasma of the sun, which is hundreds of times the size of the Earth, for a few seconds, maybe there was a network that we would think of as doing something non-trivial. Some of the research I've been doing in my lab is showing that random networks, in particular random neural networks, can do non-trivial tasks. So like the famous handwriting MNIST data set, that can be sorted to mid-90s accuracy with a single matrix multiply from a randomly drawn matrix. And on an ordinary computer, it takes only seconds to find a matrix that can do that. So we don't really need, for some problems, we don't need training or backpropagation or all of this elaborate GPU computing to find the weights. We can just sample at random and they work. So the question is, how big is that space? What's the chance that you would find a network that works at random? And so that's kind of the idea behind these automata, is exploring these simple programs, these simple random programs, and then to build some kind of like sort of butterfly net where we can run all these critters through it and then see how many of them are interesting. How many of them do something like Rule 110 or Rule 30, where we would say this is a non-trivial behavior. I'm a big fan of science fiction. I think we have to mine a lot of the classics for ideas that we can bring to science. And one of my favorite ideas, largely due to Isaac Asimov, is taking the Greek idea of Gaia, but essentially taking it seriously in a technological framework where we can think of the planet as an emerging intelligence. And then we can scale that up to what Asimov called galaxa. And you can think of then this repeating at different scales. And so do we see emergent behavior at the planetary scale, at the solar system scale, at the galactic scale? Well, how would we recognize it? What sort of techno signature would we look for? How could we do this kind of xenobiology, this SETI style search for intelligence on that scale? What would the patterns look like? Should we expect any pattern at all? As an interesting side note, when we do modern communications, we encrypt all of our traffic, which just tries to remove any visible pattern. So advanced aliens might encrypt their Wi-Fi just as often as we do, and that would mean that their patterns would be imperceivable on purpose. Two other books I want to mention is Solaris by Stanislaw Lem, and this is about an intelligent ocean on another planet, where again the planet just happens to be alive in a very different way than we think of animals typically. And then also related, the astrophysicist Hoyle, the story of the black cloud, which is a similar sort of abstract distributed intelligence on a near galactic kind of scale. So as we explore artificial intelligence and soon artificial life, combined with this Fermi paradox and xenobiology, we need to start expanding our perceptual window of what life might look like. And I think AI is helping us do that. But now we need to go back and re-explore some of these ideas. And so with that, I just want to mention that sometimes, the patterns can be unconventional, and that we have this stained glass, but on the wall, we sort of have this emergent thing. And this just happens to be an interesting pattern. But you can imagine some sort of spectral computer, some sort of optical computer emerging and mixing those wavelengths and doing something interesting. So we should keep our eyes open for interesting dynamics, new areas of physics that might support things that we previously thought only brains could support. So this reminds me of this idea of found poetry, where it sort of was already there, something interesting. And this can be where you remove other pieces, or it could be where you just happen to be looking at a menu for a restaurant somewhere and it was a bad translation and it ends up being poetic for some particular reason. So this sort of poetic for no reason is just sort of this found computer idea and this spontaneity. So I'll leave you with that. I want to thank Stephen Wolfram. I want to thank Dugan and James for putting this together. I want to thank Addie for helping connect this network. And I would thank you all for your time and attention. I appreciate it.
Great. Thank you, William.
I'd love to take some questions.
Can I ask a question?
Please.
Thank you very much, Will. That was, there are a lot of hooks in that talk for me to respond to. So I won't go too crazy, but I will start with maybe the first one that came to mind, which was when you refer to the cellular automata kind of arrangement as you use the recipe metaphor. And this idea that there's like a lookup table and that there's some sort of mechanics which is some like looking up of rules and applying them in each case. And I feel like that metaphor has is not serving us particularly well. And I kind of like this idea of more of a metaphor around heuristics, um, and that heuristics and thinking about what the actual mechanical heuristics, in some sense, of what's playing out in these different potential sets of rules are, because to me that points to kind of causal. It points much more directly to causal situations and the actual reasons why some of these patterns might have emerged. And yeah, so I wonder if you've thought much about whether the recipe metaphor is fundamental to your approach, whether if you step away from that metaphor and think about other ones, you might think differently about where you'd go with this one.
Yeah, I think it's a great point, and I think you're right about the sort of the failure of the recipe. And it makes me think of like behavior of something like ants, right? They're not following any recipe, right? They have this queen organization, but it's not the hierarchy like we think of a human organization where somebody's calling the shots and then broadcasting them. There is this sort of a coordination with the pheromones, but at the individual level, the ant is like this machine. It's like this Rube Goldberg thing where a smell hits its antenna, it turns that way. And it's not rule based any more than when you flip the switch on your vacuum cleaner, the rule says to turn on. And I don't mean like a digital one. I just mean like, no, it's a switch. It's embodied in the machinery itself. And so to think about it as rules, that's okay for sometimes, but I think we need to think about like emergent contraptions or something is what comes to mind.
Yeah, I mean, I also think that it suggests that, and if you kind of entertain the idea that life might be computation, and that computation is a kind of process of differentiation or establishing differentiation within certain constraints, then I think a lot of these patterns that we see are very easy to explain, actually, because they're almost inevitable. And the patterns that we see are kind of emerge inevitably from systems that kind of are relatively stable with respect to what they produce. Like there are a lot of different heuristics that could produce kind of the same thing. It's just a question of what the environment within which those heuristics are playing out. So then
Right.
it puts more of an emphasis on the grid, for example. So like your model right now, which is super cool, and I can't wait to play with it, is all on traditional grid. But what if we were looking at that on a different kind of grid, like Rule 30 on a more on a hex grid is just stripes.
Right.
So, like maybe Rule 30, the noise in Rule 30 is really just because there's this Rule 30 heuristic that is actually being deployed in an environment that it's actually not optimized for.
100%. And I think that we're going to see like a randomized grid, like I was saying, sort of like foamy, like bubbles, where like the squares don't have to be the same size. They don't have to have the same number of neighbors. And I suspect that we should expect nature to be more of that type. I'm a big fan of randomness. I think nature uses randomness wherever it can. And anytime you can just have like a simple, where you don't have to have a recipe, right? Where it's just, okay, just choose random and that works. Then that's a nice way to do it. So having some sort of grid that's just random or generated through some process. And I think this is a lot like what Wolfram's exploring with his physics project now.
Yeah, so there are a lot of grids that are randomized up to a certain texture. I mean, for instance, aperiodic tilings or quasicrystals. The tenfold patterns that you were looking at, the Islamic tilings, they do have decagons and pentagons and things like that. So that there are pentagonal quasicrystals that model them. But even these aperiodic tilings and stuff, these have a particular, they're random, they lack translational symmetry, but they all have a particular texture to them. So a certain number of features within them is contained.
That's
Well,
interesting.
I mean, the same thing goes for Rule 30. That there's a particular texture of downward facing triangles of various sizes that populate the thing in a particular way that's measurable. So it's not as random as static. It's a little
Right.
bit less random.
And where are these shapes? Where are these shapes coming from? There must be this kind of platonic realm where these architectures exist, and like the Sierpinski triangle showing up. That shape shows up in so many different places, like sort of different areas of mathematics. And then for that same character to show up in this story, to me is almost unreasonably interesting.
Right. In that case, it's like it's running. Maybe Ellie can speak to this. It's running the XOR pattern to make the Sierpinski triangles using one-dimensional cellular automata on a squared
It's
grid.
just like evidence. Yeah, it's like I think those triangles are evidence that there's been a negotiation between same and different. And we call that XOR, but it's really just kind of a way of acknowledging and recording the registration of whether two things are same or different, and then you get a triangle.
Wow.
Okay, so exclusive OR yields true if the inputs are decidedly different.
Yeah.
Fantastic. I put the link to the slides in the chat if anybody wants a copy and to get access to the notebooks. I also have versions of this code in Python as well.
Great. Yeah, I have some questions about your embedding. So you took you look at a 3 neighborhood segment from the 1DCA, and so your embedding was like into in that case 100 dimensions. You took a 3-dimensional space of 3 distinct color values, the colors being from 0 to 1, or was that the color space? And then
so in the black and white version, you're using the 3 neighbors, and in the color one, you're also using the 2 neighbors rather, and then also there's 3 numbers for each square.
Is that like a red, green, and blue?
Exactly.
Channels.
Yeah.
Oh, so you have color channels. Okay, so then you map that into a very high dimensional space, and then you map it back. So the mapping from, let's say, 3 dimensions to 100 dimensions will be the image of that embedding. I think will be a 3-dimensional subspace of 100 dimensionals of 100D, and then mapping that back down to 3 dimensions. When you take the composite from 3 to 100 to 3, would that be a arbitrary map, a linear mapping from 3 space to 3 space?
Well, what's nice is you have, because the tan H is in there, you get this non-linearity, and now we can get some interesting behaviors out of it. So it's not just like a linear subspace. It's really like a tiny little neural network. And I've only just been exploring simple ones, but it'd be interesting to try, larger, more complex networks in there. There's a lot of architectures that have emerged in the last decade for networks. This is just the simplest possible one, just to see how it works. But it would be neat to go through there and learn the parameters, skip connections, things like that. Looking at the fully connected versus the convolution is something I'm exploring. And then looking at like the boundary conditions, does it wrap and things like that. So there's a lot to explore with the model.
Yeah. Okay, so it is setting up like a little neural net based on the 3 inputs, going out to like 100 neurons and then coming back down to 3 neurons or something like that. Like how
exactly,
much,
yeah.
Okay.
And so you can imagine doing 2 or 3 layers, right? You could do 10 layers, whatever you might want to try.
So it's like adding computation.
In fact, a lot of those A lot of the images look like, in Stephen's paper about the one with the cat in the party hat and all the other images around that were generated by the neural net. There's some kind of quality in the images you showed, Will, from your that feel like they're navigating this space of possibilities, of pattern possibilities in a semi-structured way. But
Exactly. Yeah. What are these simple recipes that, and what do they make? And just like Wolfram categorized into the basic sort of elementary automata types, can we categorize these? Can we classify these the way we would do a taxonomy?
Oh, for sure.
And can we do that in an automated way?
Possibly, yeah. Yeah, there's got to be a way to do that.
Yeah, so we
I
could
wonder how
look
that would be
at,
automated, though.
yeah, well, we could look at some sort of entropy measure, or we could look at some sort of frequency spectrum of it to see, is it just some periodic behavior, or is there something more interesting happening?
Let's see, some questions from chat. Perpetual Science says convolutional neural network cellular automata would work best with Gaussian weighted kernels.
That sounds like an interesting thing to try.
I guess the kernel in
Yeah, I
this
think
case
that
is just over like 3 pixels, so
Well, that's also a parameter, right? So there's no reason for that. In some of the experiments, you can go out, you can change the neighborhood for that.
I like what you said about nature harnessing randomness, and that's kind of an interesting concept, is that if there's some preference for randomness over not random, and like, or is it just that it's computationally more efficient? Because that's something that some people are actually developing now, is like chips with native ability to generate random numbers. A computer to generate random numbers, quite a not very efficient process. It's like it actually has to require, if you want something to be truly random, it's actually very difficult to do that computationally. So it's actually interesting that nature might have that as an easier thing to grasp at than to try to develop something predictable.
100%. And I think particularly kind of like in an evolutionary landscape, whether it's a genetic circuit or I suspect our brain circuit leverages, if you can leverage randomness and the properties of random projections and things like that, then that's a really elegant way to do things. Because now you don't have to find the billion parameters, right? You just sample them from some process. And if that works, even if it doesn't work as well, it's still unbelievably cheap to sort of fill your system up with random numbers than it is to tune or learn, so to speak, in the traditional sense.
yeah, you mentioned the NIST is easily trained on a local computer within seconds. So can you elaborate on that?
Yeah, so you just take the image, stretch it out into a vector, and then multiply it by a matrix. And so each MNIST digit will be like 784 little pixels. You just represent that as a 784 dimensional vector. And then you multiply that by a 784 by 10 matrix. And so your dimensions sort of match up and you're left with a 10 dimensional vector. And then what you do is you just sample random vectors until that process works, essentially, right? So it's like high-speed guess and check. And you have a batch of your images and you multiply them by this matrix. You don't even need a nonlinearity or anything like that. It's just a matrix multiply. And you'll get above 90%, no problem. And it only takes seconds to find one of those suitable matrices. You can do it brute force, or you can do something like a simulated annealing, where it will adjust those weight matrices, but you don't have to have any back propagation or things like that. You don't have to have that. You just kind of evolutionary high-speed brute force it. And to me, that's really interesting because I come across, this data set, MNIST data set, is used almost like the fruit fly for machine learning experiments. It's used over and over and over again. And I saw an interesting simulation code from IBM for a quantum network that they were doing, and they ran it through MNIST, and it got like 90% when they were done. I forget the exact number. And I was saying, well, that's not, you don't know that's an interesting result because a simple random matrix can also get that level of accuracy, and it's, you know, nowhere near the sophistication of this elaborate quantum system that they were simulating. And so the point being is we need to consider these like incredibly simple programs that can do something like a machine learning task. And they're easily found.
Well, so I guess what you're describing seemed to be like a one layer neural net. You have the inputs and you have a one middle layer. So you're saying that MNIST can be done like with the input pixels, a layer between, a single layer between, and then 10 output neurons.
Yeah, and it'll get 92. You'll get 92% or whatever. You'll get lucky. If you get lucky on a single batch, you might like peak and hit like 98% accuracy. If you do it like over all the entire test data set, it'll be like 92% or something like that you can get to. Which is a pretty high score for such a like an embarrassingly simple method. And I'm surprised that math didn't know this. I mean, maybe the mathematicians did know and they say, oh, it's a linear model. Okay, they don't care. They think it's interesting. But the fact that you can do this machine learning task so simply is surprising. I don't think that's well understood or documented.
That's interesting. I mean, it's my understanding that like you set up MNIST with a bunch of convolutional neurons up front, and then start training layers of neurons behind that.
Right. So we could make any of this could be trainable, and then we can think of different loss functions to get a certain behavior. And so the really exciting thing would be to figure out what the loss function would be to get universal computation, and then force the parameters to update until you get something like rule 110. You could do that in a trivial way just by forcing it to emulate rule 110. And then you could show that this architecture is capable of universal computation that way. But I think it'd be more interesting to it's one of those things that if one of these is universal, there's probably a near infinite number of these, right? I forget which mathematician, Levin, I think he said that only a math nerd thinks 2 to the 500 is finite. Like the space of possible matrices that we have here is like astronomical, and this is like a simple model already. So if we extended this a little bit, I suspect that if we find one of these of this type that is universal, then there would be a whole class of them that would also be universal.
Yeah, so you know it depends on the landscape. Like for NIST, it's like you have these weights, you just kind of guess at the weights, and then you apply like a Monte Carlo evolution of which weights are the best, and then you get to one that minimizes the loss function pretty quickly because the landscape has like very broad drains down to sinks, down to
Exactly.
Optimal points.
So that would be cool to try to measure that landscape for systems like this.
Mm-hmm. Yeah, and you know the fact that Rule 110 can emulate a Turing machine based on the interactions of certain collider patterns in the cellular automata readout poses an interesting question for computational reducibility for that cellular automata. So, you know, it takes computation to go from one line to the next, and it's might not be reducible for 110 to say like, okay, where am I going to be 500 steps down the line? Although you set up these initial conditions, there are all these propagators that interact and bounce off of each other, and that models a certain Turing machine. And the Turing machine that it's modeling is like, it's computationally reducible in its own right, but it's easier to compute than the whole entire CA. And you can know that the CA will do the things that the Turing machine will do. So it's like, you know that all these interacting gliders will compute this Turing machine. You know what the Turing machine will do down the line. So can you not predict somehow some coarse graining at least of the CA? It's like an interesting trade-off.
I suspect that we could probably do that for like regions of the space-time, let's call it. Things like with hash life, there's some really interesting sort of like memoization kind of things that they do where they just kind of record the result. And if you have a glider over here and there's nothing in the way, like, you know, it will be over here like sometime later. And so you can just kind of take like a hash of the pattern and then just like look it up in a database. And so I think that's like an exciting direction. But these, the systems I showed clearly have these kind of glider like quasi particles. And so there's probably at least as sufficiently as complex as you would need to get this universality.
Yeah, those were very interesting. Can you show some of those again?
Yeah, for sure.
I like the ones that kind of looked organic, have like a tear or something going through them, or they look like mountains. Yeah, this is interesting. It has like 3 distinct textures to it.
Yeah, there was one that really looked like stripes on a zebra or something. That one. Yeah.
Yeah, they're this interesting mixture of like digital and organic, and sufficiently messy, right? That they might have something more richer dynamics than we might have seen before. Let me go to the notebook. You can see this now, right? Can you see this page now?
Yeah, we can see that.
Great. You can see the notebook. Okay, yeah. Yeah, I'll just scroll here. Stop if you see one that looks interesting.
What's going on here?
This one?
The yellow one. Up. That one. It's got something in the middle that looks like it's deterministic. The right half is like...
Yeah, it kind of repeats itself, but then we get some interesting stuff over here on the left, which is sort of quasi-regular.
Mm-hmm.
And so that kind of behavior would probably easily be identified with like a Fourier analysis on that last row, just to see how periodic everything is. That one's kind of neat. Because, you know, what creates these little regimes where you have these kind of stable patterns?
Mm-hmm.
And then things that like emerge, persist for a while, and then decay, which looks like particle interactions.
So the the hyperbolic tangent acts as like a sigmoid.
That's right.
Is this implementing any sort of thresholding?
Yeah, that is the threshold, is just the tan H at this point. But I've tried others. Tan H definitely gave me some, I like that one because it kept everything bounded.
Mm-hmm.
And you get interesting patterns, whereas ReLU tends to kind of like kill things off because it zeroes stuff out. But it would be interesting to try things like leaky ReLU and swish and some of the other activation functions.
What happened there? That's interesting.
This one?
There's something that like stopped, this red streak down the middle.
Yeah, and then like this little piece up top.
Yeah.
So could these be used?
So many times there's like a little bit piece of chaos that happens, and then something falls out of that solution, so to speak.
Yeah, I'm also exploring different ways of mapping the colors for the 1-dimension and the RGB version. I also have another version that's RGBA, so you can do like a 4-color channel for the alpha channel, and that lets you do like a 4-dimensional one. And then it would be interesting to sort of animate these and see them in color and stuff like that. Let's run these all again. We'll see some new ones.
Oh, this spits out random ones each time?
Yeah, so every time it runs the notebook, it's going to do a different set of weights, and then it's just going to crank these out. So these are also all new ones here. Let's look at some of these. Yeah, this is good. Like the quasi particles, like you have this streak, and then looks like something like splits off here.
Uh-huh.
And then like here, one almost emerged, but then it didn't survive.
So what rule is it trying to do in the background? Is this going through rule 30 each time, or some version of it? Or is it just...
So these are just going to create random matrices that define this mapping between the 3 to 100 and the 100 to 1.
Uh-huh.
In this case, I'm doing a normal distribution. In the other one, we did a uniform. bipolar distribution there. But they're not, so there's no goal or loss function for these. These are just truly randomized programs that are parameterized by these two matrices. And then it just runs, this is the simple little one layer neural network that determines the output. So they're not trying to emulate any particular rule. What would be interesting to try next is to put a loss function on there and force them to be the classical rules, and then maybe generalize it from there. Or give it some other sort of goal, make the bottom value random, or make the center column as random as possible, or some other function. Could we train these to draw cats or whatever it might be?
I was wondering, do you have a sense for the frequency of different types of behavior? Because I know in NKS there was, you know, Stephen Wolfram was able to like characterize how frequent class 3 automata are and class 4.
Yeah, that's still open question. And so that's what I want to try to figure out. Love if anybody has any ideas of systematically going through and doing just that, cataloging these in the different types. Like this sort of behavior, we've seen this before, right? Sort of looks like rip something that tore or something like that. We see that one. We see the simple checkerboards emerge. We see the ones that have kind of these quasi-particles. So it would be interesting to see how many different classes are there, and like you said, what are the relative ratios essentially of those types. I think that one looks like punch cards to me, so I always thought that one was cool. Right? Could you actually get these to manipulate like digital bits and actually work like a register machine essentially?
Fascinating. Another question is like, how minimal can the dimensional embedding be before you start seeing these types of behaviors? Yeah. The lower dimensions would be easy to map out.
And so that's what's fun is you guys can go and you can try this, right? You just change that to a 10 and then there we have it. Or we can change it to, let's just keep it at 3. And is there a point where we get something emerge that wasn't there before? And so we could make that a slider, right? So that's pretty interesting. It looks like a Christmas tree. That's pretty interesting. And that's just going to 3 dimensions. Or sort of keeping the 3rd dimensions, right? That one's cool. It looks like a Atari logo. And so it looks like these more often die out. And so we would want to think, is that a consequence of this, like sort of not having enough space here? And then what happens if we go in the other direction? Like if we just go up and make this hundreds or thousands, do we get anything significantly richer, or do we sort of plateau on the complexity after a few dimensions? Right? I suspect that after you get above a certain threshold, you're can be approximated as an analog space, and then adding more will probably have limiting effects.
Well, the output is analog, right? You're not.
Yeah. Well, it's, from -1 to 1 in this case. Yeah. Right. So here's 30,000 dimension, and we'd have to kind of catalog that to see, is that systematically more interesting than going to 100, let's say.
Can you make it just go to like 10 and back?
Yep. And so now we have kind of a petri dish where we can go through and explore these.
I love it.
Well, I really appreciate the opportunity to share my work.
Thanks for coming on.
Absolutely. My pleasure.
We'll wrap up. So thanks everyone for tuning in on the live stream. Thank you for your questions, and we'll see you again next time.
Thank you, everybody.
Thank you.